Look up tonight, then look down through the floor. In both directions, the solar system extends thousands of times further than the textbook ever told you. Not because the diagram was wrong, not because what's missing doesn't exist, but because the solar system is shaped like a marble, and no one has ever found a way to draw a marble on a page without leaving most of it behind. Tonight, we're going to trace the full architecture of why the disk you grew up looking at is the youngest, thinnest, smallest part of the truth, through frozen oceans and supernova-carved voids, and why the space above your ceiling tonight is not just what you live under, but what your body is quite literally made of. Before we dive in, if you love exploring the hidden architecture of space as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. Now, let's begin. You probably remember the poster. Maybe it hung on a classroom wall, maybe it lived inside a glossy textbook. The sun sits in the middle, fat and yellow. The planets trail outward in concentric rings. Mercury, Venus, Earth, Mars. Then the asteroid belt, a tidy ribbon of debris. Then Jupiter, Saturn, Uranus, Neptune, each one neatly spaced along a single flat plane. The image is clean. It is orderly, and it has shaped the way almost every person alive thinks about the space we occupy. That image is a profound distortion. It is not wrong exactly. The 8 major planets do orbit within a relatively thin plane, a disk called the ecliptic. If you could stand far above the sun and look down, you would see something remarkably close to those textbook rings. The planets trace their paths within a few degrees of one another, like grooves on an old vinyl record. This much is accurate. But the poster commits its deception not through what it shows, but through what it leaves out. It shows the disk. It does not show what lies above the disk or below it. It draws the solar system as if it were two-dimensional, when in truth, the structures extending vertically, straight up from the sun's north pole, straight down from its south pole, dwarf the planetary orbits by factors of thousands. Here is one way to feel the scale of that distortion. Neptune, the outermost planet, orbits at roughly 30 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. So Neptune's orbit stretches to about 4.5 billion kilometers. That is the edge of what the textbook poster shows. That is where the map ends and the white margin of the page begins. But the Sun's gravitational influence, the true boundary of the solar system, extends to nearly 100,000 astronomical units. That is more than 3,000 times farther than Neptune. And the structures filling that immense volume are not flat. They are not confined to a disk. They form a sphere, and then another sphere, and then a bubble shaped by forces that have nothing to do with planetary orbits at all. The poster, in other words, shows you the thinnest possible slice of the solar system and calls it the whole thing. Tonight, we leave the poster behind. Start with the disk itself. The ecliptic plane, the flat sheet in which the planets orbit, is not a physical surface. It is a mathematical convenience, a reference plane defined by Earth's own orbit around the Sun. The other planets do not orbit exactly within it. Mercury tilts 7 degrees off the ecliptic. Pluto, before its reclassification, tilts a full 17 degrees. Even the larger planets have small inclinations. Jupiter at 1.3 degrees, Saturn at 2.5. These are modest angles, and they reinforce the impression that the solar system is essentially flat. But modest angles applied to enormous distances produce enormous vertical excursions. Saturn, tilted just 2.5 degrees from the ecliptic, rises and falls hundreds of millions of kilometers above and below that imaginary plane over the course of a single orbit. The flatness is statistical. Up close, the disk has depth. And then there is the matter of what the planets are made of and how they got here. The reason the major planets orbit within a thin plane is historical, not geometric. Roughly 4.6 billion years ago, the solar nebula, the vast cloud of gas and dust that collapsed to form the Sun, flattened into a rotating disk as it contracted. Angular momentum forced the material into a plane, and the planets formed within that plane by accretion. The process was orderly in 2 dimensions, but in 3 dimensions, the story is far messier. Not everything stayed in the disk. Some material was flung outward, gravitationally scattered by the giant planets into orbits that tilted wildly, reaching far above and below the ecliptic. That scattered material did not vanish. It settled into vast, 3-dimensional structures that surround the flat planetary disk, the way an ocean surrounds a coral reef. The first of those structures sits just beyond Neptune. The Kuiper Belt, a vast ring of icy bodies stretching from roughly 30 to 50 astronomical units, is often drawn as another flat ribbon in the ecliptic plane, a second asteroid belt. Everyone knows the Kuiper Belt as a disk of frozen debris. The textbook answer is tidy, a flat donut of ice and rock, the source of short-period comets, the home of Pluto and its kin. That picture is almost entirely wrong in one critical respect. The Kuiper Belt is not flat. Its objects orbit with inclinations that span a wide range, some tilted 30 degrees or more off the ecliptic. If you could see every known Kuiper Belt object at once, you would not see a ring. You would see a thick, puffy torus, a donut with a serious vertical extent, bulging above and below the ecliptic, like a cushion compressed at its center. Some of the most scientifically significant objects in the Kuiper Belt are the ones that stray farthest from the plane. The dwarf planet Eris, discovered in 2005 by astronomer Mike Brown of the California Institute of Technology, and his colleagues Chad Trujillo and David Rabinowitz, using images taken at Palomar Observatory, orbits at an inclination of 44 degrees. At the high point of its orbit, Eris rises so far above the ecliptic plane that it would be completely invisible to any survey that looked only along the flat disk. It was found precisely because Brown's team searched above and below the traditional plane. And Eris is not alone. Dozens of trans-Neptunian objects occupy orbits that take them far out of the ecliptic, tracing looping paths that rise and fall through a vertical space many billions of kilometers deep. Then there is Sedna, with a perihelion of 76 to 77 astronomical units, far beyond Neptune's influence, and a semi-major axis of roughly 500 astronomical units. Sedna occupies an orbit that no known dynamical process in the current solar system fully explains. Its orbit is so elongated that it spends most of its roughly 11,400-year journey at extreme distances from the Sun, in a region of space that is gravitationally detached from the planets, but not yet part of the true Oort Cloud. Sedna exists in a kind of orbital no-man's land, too far for the planets, too close for the comets, sweeping outward to enormous distances from the Sun. Its very existence is a clue that the space above and below the solar system is not empty. It is structured. Something shaped Sedna's orbit, and the leading explanations involve gravitational encounters that happened when the Sun was young. Perhaps a passing star, perhaps the tidal influence of the Sun's birth cluster. Forces that operated not in the plane, but perpendicular to it. Pause here, because the map is about to change dramatically. So far, everything we have discussed, the planets, the Kuiper Belt, Sedna, occupies a region within a few hundred astronomical units of the Sun. On the scale of the full solar system, that is a pinprick. What comes next is incomprehensibly larger. Above the Kuiper Belt and below it, extending in every direction like a vast dark shell, lies the Oort Cloud. In 1950, Dutch astronomer Jan Oort proposed the existence of a spherical reservoir of comets at the edge of the solar system. He was trying to solve a puzzle. Long-period comets, comets that take thousands or millions of years to complete a single orbit, arrive from every direction, not just from the ecliptic. They plunge inward from above, from below, from angles that have no relationship to the flat planetary disk. If comets came only from the Kuiper Belt, they would arrive roughly in the ecliptic plane. But they do not. They arrive isotropically, from all directions equally. Oort concluded that there must be an enormous, roughly spherical cloud of icy bodies surrounding the Sun at distances of tens of thousands of astronomical units. This cloud, now bearing his name, is thought to contain between 1 trillion and 10 trillion cometary nuclei, formed in the primordial solar nebula. Observations and computer modeling have contributed to a detailed understanding of its structure and dynamics, and it is thought to be the source of the long-period comets. The Oort Cloud is not visible. No telescope has ever directly imaged a single object within it. The bodies are too small, too dark, and too far away. Everything we know about the Oort Cloud is inferred, from the trajectories of comets that fall inward, from computer simulations of how the solar system evolved, from the statistics of orbital mechanics applied across billions of years. And yet the evidence is overwhelming. The Oort Cloud is a large shell of icy bodies surrounding the solar system at heliocentric distances of roughly 1,000 to 100,000 astronomical units. The new long-period comets have a nearly isotropic distribution of orbital inclinations, suggesting that the outer Oort Cloud is roughly spherical. 100,000 astronomical units. That number needs context. Neptune orbits at 30 astronomical units. The Kuiper Belt ends at roughly 50. The Oort Cloud's outer edge, at 100,000 astronomical units, is approximately 1.6 light-years from the Sun. The nearest star, Proxima Centauri, is 4.2 light-years away. The Oort Cloud, in other words, extends more than a third of the way to the nearest star. It is the solar system's true boundary, and it is emphatically not flat. It is a sphere, a hollow shell of frozen objects that wraps around the Sun in every direction, above and below, north and south, with no preference for the ecliptic at all. Think about that for a moment. The flat disk of planets that you were taught is the solar system occupies at most the innermost 1,000th of the solar system's true radius. The remaining 99.9% is vertical. It is above you and below you. It is a sphere of ice and silence, and it has been there since the planets were born. This is worth pausing on. The solar system is not shaped like a disk. It is shaped like a marble, a dark, frozen marble with a bright, thin line running through its center. The line is the ecliptic. The planets live on the line. Everything else, by volume, by count, by sheer spatial dominance, lives above and below it. And the Oort Cloud is not even the largest structure that extends vertically from the Sun. Because surrounding the Oort Cloud, pressing against it from the outside, is a boundary that the Sun itself creates. A boundary shaped not by gravity, but by wind. The Sun is not quiet. It appears calm from Earth, a steady disk of light, rising and setting with comforting predictability. But the Sun is a thermonuclear furnace that continuously hurls matter into space. Every second, it releases roughly 1.5 million tons of charged particles. protons, electrons, alpha particles, in a ceaseless outflow called the solar wind. This wind races outward in all directions at speeds between 300 and 800 kilometers per second. It does not stop at Mars. It does not stop at Jupiter. It does not stop at Neptune. It rushes past the Kuiper belt, past the inner edge of the Oort Cloud, and keeps going until it finally encounters something it cannot push through. That something is the interstellar medium, the thin magnetized gas that fills the space between the stars. The solar wind, powerful as it is, eventually loses enough pressure that it can no longer hold back the interstellar wind pressing inward. At that boundary, a vast bubble forms. Inside the bubble, the sun's particles and magnetic field dominate. Outside the bubble, interstellar material takes over. This bubble is called the heliosphere, and it is enormous. It encompasses the entire solar system, spanning such a vast distance that only 2 spacecraft have ever managed to leave it. The heliosphere extends in every direction, above the ecliptic, below it, ahead of the sun's motion through the galaxy, and behind it. It is not confined to the plane of the planets. It wraps around the solar system from top to bottom, a magnetic cocoon spun from solar wind. And its shape, for more than 60 years, was thought to be straightforward. Everyone assumed the heliosphere looked like a comet. The prevailing picture was one of a comet-shaped structure, with a rounded nose facing the direction the solar system moves through interstellar space, and a long tail streaming behind. The nose would be compressed by the interstellar wind, the tail stretched and tapered. It was elegant. It was intuitive, and new data suggest it may be wrong. Combined measurements from NASA's Voyager spacecraft, the Cassini mission, and the Interstellar Boundary Explorer, IBEX, suggest that our Sun and planets are surrounded by a giant rounded system of magnetic field, calling into question the alternate view of the solar magnetic fields trailing behind the Sun in the shape of a long comet tail. The interstellar magnetic field, it turns out, is far stronger than anyone predicted. Voyager 1 measured it at roughly half a nanotesla, about twice the expected value. Voyager 2 found an even stronger field, around 0.7 nanotesla. That unexpectedly powerful magnetic field appears to act like a straitjacket, suppressing the expansion and contraction of the heliosphere and preventing the formation of a long tail. The heliosphere, it seems, is rounder than we imagined. Some researchers even propose it could be croissant-shaped, with the Sun in the middle and 2 jet-like lobes on either side, formed by the Sun's own magnetic field, funneling plasma into twin structures above and below the ecliptic. The shape remains genuinely uncertain. As a 2024 paper in the Astrophysical Journal noted, the shape of the heliosphere remains largely uncertain due to the lack of in situ measurements. Additional data and modeling are needed to ascertain the precise geometry, and that data is now arriving. On September 24, 2025, NASA launched the Interstellar Mapping and Acceleration Probe IMAP aboard a SpaceX Falcon 9 from Kennedy Space Center in Florida. Led by Princeton University professor David McComas, the IMAP mission carries 10 scientific instruments designed to map the heliosphere's boundaries with 30 times the resolution of its predecessor, IBEX. The spacecraft reached its destination at Lagrange Point 1 in January 2026 and began its primary science mission on February 1, 2026. Over the coming years, IMAP will chart the vast range of particles, dust, ultraviolet light, and magnetic fields in interplanetary space, constructing the most detailed map of the heliosphere's boundary ever assembled. But here is the point that matters for our vertical journey. Whether the heliosphere is round or comet-shaped or croissant-shaped, it extends above and below the ecliptic plane by staggering distances. The heliosphere's boundary, the heliopause, lies roughly 90 to 120 astronomical units from the Sun in the direction the solar system is traveling, and likely a similar distance, or even farther, in the perpendicular directions, including straight up and straight down relative to the ecliptic. That means the solar wind's protective bubble reaches hundreds of billions of kilometers above your head and hundreds of billions of kilometers below your feet. It is not a thin film. It is a three-dimensional fortress of charged particles, and you are inside it right now. Take a moment to look up at the ceiling or at the sky if you are near a window. Everything your eye can see, every star, every visible planet, is inside this bubble. The heliosphere wraps around all of it, pressing outward against the dark. Now we cross the boundary. Imagine traveling straight up from the Sun, perpendicular to the ecliptic plane, through the Oort Cloud's frozen shell until you reach the heliopause. At roughly 100 astronomical units above the ecliptic, the character of space changes. The solar wind, which has been thinning steadily as it expands, slows abruptly. It passes through a boundary called the termination shock, where it drops from supersonic to subsonic speeds, a sudden deceleration so violent that the plasma heats dramatically. Beyond the termination shock lies the heliosheath, a turbulent region where the slowed solar wind piles up against the incoming interstellar medium. The heliosheath is thick, perhaps 30 to 50 astronomical units deep. Passing through it, the solar wind grows weaker and weaker until finally, at the heliopause, it stops entirely. The Sun's influence ends, and something else begins. What waits beyond the heliopause, directly above and below our solar system, is not empty space. It is the interstellar medium, and the particular patch of interstellar medium surrounding our Sun has a name, a temperature, and a history. The Sun is located at the edge of a low-density cloud called the local interstellar cloud, sometimes known informally as the local fluff. This cloud has a temperature of approximately 7,000 Kelvin, surprisingly close to the temperature of the Sun's visible surface, though the comparison is misleading because the cloud is extraordinarily thin. Its density is only about 0.3 atoms per cubic centimeter. For perspective, the air you are breathing right now contains roughly 25 quintillion molecules per cubic centimeter. The local interstellar cloud is a near-perfect vacuum by any human standard. But by interstellar standards, it is not empty. It is 6 times denser than the gas filling the larger cavity it sits inside. The solar system is estimated to have entered the local interstellar cloud somewhere between roughly 10,000 and 130,000 years ago. The exact entry time remains uncertain, and current estimates suggest it will remain within it for another few thousand to 20,000 years. The cloud is flowing outward from the direction of the Scorpius-Centaurus stellar association, a region of active star formation roughly perpendicular to the Sun's own direction of travel through the galaxy. The interstellar wind, the flow of gas from this cloud, is what presses against the heliosphere from the outside, shaping the bubble's geometry. Above the ecliptic and below it, this wind pushes inward with the same pressure, which is one reason the heliosphere extends roughly equally in the vertical directions, even though it may be compressed horizontally by the Sun's forward motion. In 2019, researchers found traces of interstellar iron-60, a radioactive isotope not produced in the solar system, in Antarctic snow. A follow-up 2026 study published in Physical Review Letters by Dominic Koll and colleagues at the Helmholtz Zentrum Dresden-Rossendorf analyzing 40,000 to 80,000-year-old Antarctic ice cores, traced its source to the local interstellar cloud itself, providing direct physical evidence that material from outside the heliosphere reaches Earth's surface. Atoms forged in ancient stellar explosions, drifting through interstellar space for millions of years, sifting down through the atmosphere and settling on Antarctic ice. The space above and below the solar system is not merely present. It is raining down on you, one atom at a time. And yet, the local interstellar cloud is a small thing. It is a wisp, a diffuse puff of partially ionized gas, perhaps 15 to 20 light-years across. It is one of approximately 15 such clouds that collectively form what astronomers call the Cluster of Local Interstellar Clouds, or CLIC. These clouds float within a much larger structure, a structure that defines the vertical architecture of our neighborhood far more profoundly than the Oort Cloud or the heliosphere. Picture yourself standing on an ocean floor looking up. The water above you is thin and warm, almost invisible. But the ocean itself, the vast basin that contains the water, is immense. The local interstellar cloud is the water. The basin is called the local bubble. The local bubble is a region of extraordinarily low-density gas extending at least 300 light-years from the Sun in most directions. The average density inside it is roughly 0.01 atoms per cubic centimeter, 100 times thinner than the typical interstellar medium in the Milky Way's disk. It is, in the most literal sense, a void, a cavity in the galaxy's gas, a place where the normal interstellar medium has been swept away, leaving behind a near vacuum filled with faint, hot X-ray emitting plasma. What carved this void? The answer lies in a particular direction in the sky, toward the constellations Scorpius and Centaurus. About 15 to 16 million years ago, two star clusters, Upper Centaurus Lupus and Lower Centaurus Crux, formed in the Scorpius-Centaurus OB association, producing dozens of massive, hot, short-lived stars. These stars burned through their fuel in just a few million years, and then they exploded. Evolutionary synthesis models indicate that the association must have experienced roughly 20 supernova explosions in the last 10 to 12 million years. Each detonation unleashed a blast wave that slammed into the surrounding interstellar gas, heating it, accelerating it, and pushing it outward. Over millions of years, these successive explosions hollowed out a vast cavity, the local bubble. And the Sun, drifting through the galaxy on its own orbit, entered this bubble roughly 7 to 8 million years ago. The bubble extends in 3 dimensions. It is not confined to the galactic plane. It reaches above and below the Sun by hundreds of light years. At high galactic latitudes, straight up toward the galaxy's north pole and straight down toward its south, the bubble's walls are defined by gas and dust that were displaced by the supernova explosions, pushed outward and upward until they piled against the denser material of the galaxy's upper and lower atmosphere. In some directions, the bubble may be open-ended, forming a chimney that vents hot gas out of the galactic plane entirely, connecting the disk of the Milky Way to the hotter, thinner halo above and below. This is a profound shift in perspective. The space above and below the solar system is not simply the continuation of the interstellar medium. It is a cavity, a wound in the galaxy, blasted open by dead stars, still hot, still glowing faintly in X-rays, still expanding at its edges. And the Sun sits near the middle of this cavity, drifting through it like a lantern inside a cathedral. Stop here for a moment, because the scale has just changed. We began at the ecliptic, the flat plane of the planets, a few billion kilometers across. We rose through the Kuiper Belt's puffy torus, through the Oort Cloud's trillion-body sphere, stretching 1.6 light-years in every direction. We passed through the heliosphere's magnetic boundary, stepped into the local interstellar cloud's warm haze, and now we find ourselves inside a 300 light-year void, a bubble blown by ancient explosions. Each layer is vastly larger than the one before. Each layer is invisible from inside the previous one, and each layer, critically, extends above and below the ecliptic plane. The solar system's vertical architecture is not a single column. It is a series of nested spheres, each one dwarfing the last. The next sphere is the galaxy itself. And when you look at the Milky Way from the perspective of vertical structure, when you ask what lies above and below the galactic plane, not just along it, the answer reshapes everything you thought you knew about the night sky. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years in diameter. You have seen the images, a glowing pinwheel of stars, gas and dust viewed from above. Beautiful, flat, and, once again, profoundly misleading. The disk of the Milky Way, the plane where most stars, gas and dust reside, is thin compared to its diameter. The stellar thin disk has a scale height of roughly 300 to 400 parsecs, which means that the density of stars drops by a factor of roughly 2.7 for every 300 to 400 parsecs you travel above or below the midplane. 1 parsec is 3.26 light-years, so the thin disk's scale height is roughly 1,000 to 1,300 light-years. Most of the galaxy's visible mass is concentrated within a slab a few thousand light-years thick. Compared to the galaxy's 100,000 light-year diameter, the disk is extraordinarily flat, like a compact disk, or a crepe, or a sheet of paper seen from the side. But the galaxy does not end at the edge of the thin disk. Above the disk and below it, stars continue, fewer, older, dimmer, but present. This is the thick disk, a population of stars with a scale height roughly 2 to 3 times that of the thin disk, extending several thousand light-years above and below the midplane. The thick disk's stars are, on average, older and more metal-poor than the thin disk's stars. They were born in an earlier epoch of galactic history, and their orbits are more vertically extended, bobbing higher above and plunging deeper below the midplane with each orbit around the galactic center. And beyond the thick disk, the galaxy still does not end. Extending tens of thousands of light-years above and below the midplane is the stellar halo, a roughly spherical cloud of ancient stars and globular clusters that predates the disk entirely. The halo contains only about 1% of the Milky Way's stellar mass, but it occupies a volume hundreds of times larger than the disk. Its stars are among the oldest in the galaxy, some nearly as old as the universe itself. They orbit not in the neat circles of the disk, but in wildly eccentric, often highly inclined paths, plunging through the disk and rising far above it before falling back. The Sun lives inside the thin disk, but the Sun is not stationary within it. The Sun orbits the galactic center at roughly 230 kilometers per second, completing one full revolution every 225 to 250 million years, a period sometimes called a galactic year. Superimposed on that circular motion is something far more relevant to our vertical journey. The Sun oscillates. It bobs up and down through the galactic plane like a horse on a carousel, driven by the gravitational pull of the mass concentrated in the midplane. When the Sun is above the plane, the combined gravity of stars, gas, and dust below it pulls it back down. When it passes through the midplane and emerges below, the same restoring force pulls it back up. The result is a slow, stately oscillation, a harmonic motion through the galaxy's vertical axis. In 1985, astrophysicists John Barkall and Safi Barkall published a landmark study in Nature calculating the parameters of this oscillation. They found acceptable half periods for the vertical oscillation that range from 26 to 37 million years, with maximum heights above the plane from 49 to 93 parsecs, roughly 160 to 300 light-years. The Sun, in other words, rises about 200 light-years above the galactic midplane, slows, stops, and then falls back through, descending 200 light-years below the midplane before rising again. One full cycle, up, through, down, through, and back up, takes roughly 52 to 74 million years. Right now, best estimates place the Sun approximately 15 to 25 parsecs, roughly 50 to 80 light-years, above the galactic midplane. We are near the top of our current bounce, approaching the apex of an oscillation that began tens of millions of years ago. If you could watch the Sun's motion from the side, compressed into a time-lapse spanning hundreds of millions of years, you would see it tracing a gentle sine wave through the galaxy's disk, threading the plane again and again, rising and falling with a rhythm set by the density of matter in the midplane. This oscillation is not merely geometric. It may have shaped the history of life on Earth. In 1985, Richard Stothers of NASA's Goddard Institute for Space Studies proposed that the Sun's vertical oscillation modulates the rate of impact cratering on Earth. The reasoning is elegant and unsettling. The midplane of the galaxy is where the density of interstellar clouds, molecular gas, and other perturbing objects is highest. Each time the Sun passes through the midplane, the Oort Cloud is subjected to stronger gravitational tides and closer encounters with interstellar clouds. These perturbations can dislodge comets from their distant, stable orbits and send them plunging inward toward the inner solar system. More midplane crossings, more comet showers. More comet showers, more impacts on Earth. The idea remains debated. The cratering record is noisy, the periodicity is imprecise, and the link between galactic oscillation and mass extinctions is far from proven. Some researchers find the correlation compelling. Others argue it is statistical noise. But the underlying physical mechanism is real. The space above and below the galactic plane is not uniform. The density of matter changes with height, thickest at the midplane, thinner as you rise. And the Sun's slow vertical journey through that changing density exposes the solar system to varying levels of gravitational disturbance. The Oort Cloud, that fragile sphere of frozen bodies, feels every change. Imagine the solar system as a boat on an ocean. The ocean's surface is the galactic midplane. The boat does not stay level. It rides a slow swell, rising and falling over tens of millions of years. At the crest of the swell, the water is calm. The density of interstellar material is low. The gravitational tugs are gentle. The Oort Cloud rests undisturbed. But as the boat descends toward the trough, the water thickens. The currents grow stronger. The comets stir. And when the boat passes through the surface itself, when the Sun crosses the galactic midplane, the disturbance is at its peak. We are currently near the crest. The Sun is above the midplane, in a region of relatively low interstellar density. The local bubble provides additional insulation, an extra cavity of near vacuum that further reduces the density of material surrounding the solar system. For the moment, the Oort Cloud is quiet. But in roughly 30 million years, the Sun will begin its descent. It will fall back through the midplane, pass through denser regions of the galaxy, and the Oort Cloud will feel it. That is a long time from now. It is a rhythm measured in geological epochs, not human lifetimes. But it is real, and it connects the space above and below your head to the history of every living thing on this planet. Now we ascend further. We have left the solar system entirely, left the Oort Cloud, left the heliosphere, left the local interstellar cloud, left even the vast emptiness of the local bubble. We are rising vertically, straight up from the galactic plane, and the structures we encounter now belong not to the Sun, but to the Milky Way itself. The first thing you notice as you climb above the thin disk is that the stars do not simply vanish. The bright, young blue stars of the disk, the ones that trace the spiral arms, the ones that populate the Scorpius-Centaurus association and powered the supernovae that carved the local bubble, those disappear quickly. They are confined to the thinnest part of the disk, hugging the midplane like fog in a valley. But older stars persist. Red giants, orange dwarfs, ancient sun-like stars with orbits that carry them far above the plane. These continue for thousands of light years above the disk. They form the thick disk, a population that was first clearly identified in the 1980s through careful surveys of stellar chemistry and kinematics. The thick disk's stars are, on average, 10 to 12 billion years old. They were born when the Milky Way was young, before the thin disk had fully settled, and their orbits retain the memory of that earlier, more turbulent era. They bob higher, plunge deeper, and trace paths through three-dimensional space that the younger, thinner disk stars never follow. Rise higher still, 5,000 light-years above the midplane, 10,000, and even the thick disk begins to fade. But the galaxy is not finished. Scattered through a vast, roughly spherical volume extending 50,000 light-years or more above and below the disk, are the oldest objects in the Milky Way, globular clusters and lone halo stars. The globular clusters are spectacular, dense, gravitationally bound swarms of hundreds of thousands of stars, many of them nearly as old as the universe. The Milky Way hosts roughly 150 known globular clusters, and they orbit not in the plane, but in wildly tilted, often highly eccentric paths that carry them far above the disk and far below it. Some reach heights of 100,000 light-years above the midplane. They are the galaxy's vertical sentinels, tracing orbits that predate the disk itself. Among the most studied is 47 Tucanae, visible from the southern hemisphere as a faint, fuzzy star near the small Magellanic Cloud. It lies roughly 13,000 light-years from the Sun and about 11,000 light-years below the galactic plane. Its stars are roughly 11 to 12 billion years old. It has been orbiting the galaxy for nearly the entire history of the cosmos, plunging through the disk, rising above it, falling below it, in a rhythm far slower and grander than the Sun's own gentle oscillation. Another, NGC 7078, also known as Messier 15, sits roughly 33,000 light-years from Earth in the constellation Pegasus. Recent simulations have examined the gravitational influence of such clusters on the Oort Cloud during close passages, a reminder that the structures far above and below the galactic plane are not merely distant curiosities. They interact with the solar system, gravitationally, across time spans measured in billions of years. But here is where the picture takes a turn that most people never encounter, even in advanced astronomy courses. The stars, all of them, from the youngest blue supergiants in the thin disk to the oldest red giants in the halo, account for only a small fraction of the Milky Way's total mass. The galaxy's dominant component, by mass, is invisible. It emits no light, absorbs no light, and interacts with ordinary matter only through gravity. It is dark matter, and it forms a halo that extends far beyond the visible galaxy in every direction, including, critically, above and below the disk. The textbook answer is that the Milky Way is a disk of stars about 100,000 light-years across. That picture is almost entirely wrong when it comes to the galaxy's true extent. The dark matter halo is thought to extend roughly 950,000 light-years from the galactic center, almost 1,000,000 light-years, in a roughly spherical distribution. The disk of visible stars, from this perspective, is a thin, bright streak embedded inside an enormous dark sphere. If you could somehow perceive dark matter, if it glowed even faintly, the night sky would look nothing like what you see. The galaxy would appear as a vast, dim orb, with a narrow band of light running through its equator. The vertical extent would dominate. Above you and below you, the dark matter halo would stretch for hundreds of thousands of light-years, outweighing all the stars, all the gas, all the dust, all the planets, and all the black holes combined by a factor of roughly 10 to 1 or more. No one knows what dark matter is. We know it is there because of its gravitational effects, the rotation curves of galaxies, the bending of light around massive clusters, the patterns in the cosmic microwave background all demand its existence. But its particle nature remains one of the deepest unsolved problems in physics. It could be a new kind of particle, something outside the standard model. There could be many kinds of particles. It could be something stranger still. We do not know. What we do know is that it extends above and below the galactic disk in quantities that dwarf everything visible, and that it defines the gravitational potential well in which the entire galaxy, disk, halo, globular clusters, and our own solar system sits. The Sun's vertical oscillation through the galactic plane, which we discussed earlier, is driven in part by this dark matter. The restoring force that pulls the Sun back toward the midplane depends on the total mass density near the plane, and dark matter contributes to that density. In a very real sense, the invisible matter above and below the disk is shaping the trajectory of every star in the galaxy, including ours. The space above you is not empty. It is full of something you cannot see, something that outweighs everything you can see, and it is pulling on you right now. Pause here, because we are about to encounter something that was not discovered until the 21st century. Something that fundamentally changed our understanding of what exists above and below the Milky Way's disk. In 2010, astrophysicists Meng Su, Tracy Slatia, and Douglas Finkbeiner at Harvard University were analyzing data from NASA's Fermi Gamma Ray Space Telescope when they found something no one had predicted. Rising from the center of the Milky Way, extending roughly 25,000 light-years above the galactic plane and 25,000 light-years below it, were two enormous, sharply defined lobes of high-energy gamma-ray emission. They looked, in the cleaned images, like two vast bubbles inflated from the galactic center, one pushing north, one pushing south, each one roughly as tall as the distance from the Sun to the galactic center itself. These structures are now called the Fermi bubbles, and their discovery was a genuine shock. No model of the Milky Way had predicted their existence. They are among the largest coherent structures in the galaxy, and they exist entirely above and below the disk, perpendicular to the plane in which you live. The edges of the Fermi bubbles are remarkably sharp. The transition from the bubble interior to the surrounding halo gas occurs over a distance that is tiny compared to the bubble's overall size. Inside, the gas is hot and energetic, emitting gamma rays and microwaves. The energy required to inflate these bubbles is staggering, estimated at roughly 10 to the power of 55 to 56 ergs, equivalent to the energy output of millions of supernovae. Something at the galactic center, at some point in the past several million years, released a cataclysmic amount of energy straight up and straight down. Two explanations have been proposed, and the debate is not settled. Some researchers think the bubbles were inflated by a burst of intense star formation near the galactic center, a period when the central few hundred light-years of the galaxy were producing stars at an unusually high rate, driving powerful winds vertically out of the disk. Others think the energy source was the Milky Way's central supermassive black hole, Sagittarius A star, which may have undergone a period of active accretion several million years ago, producing relativistic jets that punched through the disk and inflated the bubbles from the inside. Both mechanisms are physically plausible. Both can produce structures of roughly the right size and energy. And without better data, we cannot yet distinguish between them. The Fermi bubbles are invisible to the naked eye. They emit gamma rays and microwaves, not visible light. But they are there, right now, towering above and below the center of the galaxy. If you could see gamma rays, the night sky would be dominated not by the flat band of the Milky Way, but by two colossal pillars of light, rising from the galactic center and reaching halfway to your position in the disk. The galaxy, seen in gamma rays, is not flat at all. It is vertical. It is columnar. It is shaped more like an hourglass than a disk. And the Fermi bubbles are not the only structures above and below the galactic center. In 2020, the Eurosighter X-ray telescope, a joint German-Russian mission aboard the Spectre RG spacecraft, revealed even larger structures in the X-ray band. These Eurosighter bubbles extend roughly 45,000 light-years above and below the galactic plane, dwarfing the Fermi bubbles themselves. They may represent an older, more expanded version of the same phenomenon, the same energy release seen at a later stage of expansion when the material has cooled enough to emit X-rays rather than gamma rays. Or they may be a separate event entirely. The relationship between the Fermi bubbles and the Eurosighter bubbles is one of the most active areas of research in galactic astrophysics today. Consider what this means for the vertical structure of the galaxy. The disk, the flat, bright band of stars, is roughly 2,000 light-years thick. The Fermi bubbles extend 25,000 light-years above and below it. The Eurosighter bubbles reach 45,000 light-years. The dark matter halo extends 300,000 light-years or more. The vertical dimension of the Milky Way is not an afterthought. It is not a footnote to the flat disk. It is where the most energetic, most mysterious, and most massive structures reside. Imagine yourself standing on the galactic plane, looking up. Beneath your feet, stars stretch 1,000 light-years down. Above your head, stars thin and fade over a few thousand light-years. But beyond them, invisible to your eyes, the Fermi bubbles rise in gamma-ray light, towers of energy 25,000 light-years tall. Beyond those, the Eurosighter bubbles glow in X-rays, 45,000 light-years. Beyond those, dark matter fills a sphere 300,000 light-years across. And beyond that, beyond the dark matter halo itself, the galaxy's influence reaches further still into a region of hot, diffuse gas called the circumgalactic medium. The circumgalactic medium is the atmosphere of the galaxy. It is a vast, nearly invisible halo of hot gas, primarily ionized hydrogen, extending perhaps 600,000 light-years from the Milky Way's center in all directions. Its temperature is roughly 1 to 2 million Kelvin, hot enough to emit X-rays but so thin that it is extraordinarily difficult to detect. Its total mass may rival or exceed the mass of all the stars in the galactic disk combined. It is the Milky Way's largest baryonic component, the biggest reservoir of normal non-dark matter, and it exists almost entirely above and below the visible galaxy. The circumgalactic medium is not static. It is fed from below by galactic winds, outflows driven by supernovae, by star formation, by the energy released when gas falls into black holes. The Fermi bubbles, if they are driven by the central black hole or by central star formation, may be injecting energy and material into the circumgalactic medium right now. And from above, the circumgalactic medium is fed by accretion. Cold gas from the intergalactic medium, material from satellite galaxies, debris from ancient mergers, all of it falling inward, heating up and joining the hot halo. One of the most dramatic examples of this accretion is visible in the southern sky. The Magellanic Stream, a long, arcing ribbon of neutral hydrogen gas, stretches more than 100 degrees across the sky, trailing behind the large and small Magellanic Clouds as they orbit the Milky Way. The stream extends far below the galactic plane, reaching distances of more than 180,000 light-years from the galactic center. It is being stripped from the Magellanic Clouds by the gravitational tidal forces of the Milky Way and by the ram pressure of the circumgalactic medium itself, the hot halo gas acting like a headwind, pulling gas off the smaller galaxies as they plow through it. The Magellanic Stream is a river in the sky, a river of hydrogen flowing through the space below the galactic disk, feeding the Milky Way with fresh gas that will eventually settle into the disk and form new stars. It is the vertical food chain of the galaxy made visible. Material falls from above. It heats, cools, fragments, and descends. It joins the disk. It forms stars. Those stars live, die, and explode, driving winds that push material back up into the halo. The cycle continues endlessly in a vertical circulation pattern that has operated for billions of years. Above the disk, the same process plays out with different actors. High-velocity clouds, clumps of neutral hydrogen moving at speeds inconsistent with the rotation of the galactic disk, rain down onto the Milky Way from above and below. Their origins are debated. Some may be fragments of the circumgalactic medium, cooling and condensing as they fall. Some may be debris from ancient interactions with other galaxies. Some may be material that was ejected from the disk by supernova-driven winds and is now falling back, completing a cycle called the galactic fountain. Whatever their origin, these clouds demonstrate that the space above and below the galaxy is not passive. It is dynamic. It is raining. Gas falls in, gas is blown out, and the galaxy breathes vertically with every cycle of star formation and stellar death. This is the solar system's true context. You live on a planet orbiting a star embedded in a thin disk, but that disk is sandwiched between towers of gamma-ray light, enveloped in a dark matter sphere, and surrounded by a hot gaseous halo that extends for hundreds of thousands of light-years in every vertical direction. The flat poster on the classroom wall did not merely leave out the Oort Cloud, it left out the architecture of the cosmos. And yet, we are not finished climbing. Because the Milky Way itself, disk, halo, bubbles, dark matter, circumgalactic medium and all, is not alone. It is part of a larger structure. And that structure too has a vertical axis. It has an above and a below. And what lives there is stranger than anything we have encountered so far. Take stock of where we are. We began at the ecliptic, the thin, bright plane of the planets, and we have climbed through 7 nested layers, each one larger than the last. The Kuiper Belt's thick torus, the Oort Cloud's frozen sphere, reaching 1.6 light-years in every direction, the heliosphere's magnetic boundary, the local interstellar cloud's warm haze, the local bubble's 300 light-year void, the galactic disk, thick disk, and stellar halo. The Fermi bubbles and Aerosita bubbles rising tens of thousands of light-years above the galactic center. The dark matter halo stretches 300,000 light-years. The circumgalactic medium extends even farther. Each layer has been invisible from inside the one below it. Each layer has dwarfed the previous one. And now we step beyond the Milky Way itself. The Milky Way is not alone in space. It is the largest member of a small collection of galaxies called the Local Group, a gravitationally bound association of more than 80 known galaxies spread across roughly 10 million light-years. The Local Group has structure. It has a shape. And that shape, like everything else we have encountered, extends vertically. The two dominant members of the Local Group are the Milky Way and the Andromeda Galaxy, separated by approximately 2.5 million light-years. Most of the remaining galaxies are small, dwarf galaxies, irregular galaxies, faint and dim and easily overlooked. But their distribution in space is not random. Many of the Milky Way's satellite galaxies, the smaller galaxies that orbit it, appear to lie in a thin plane. This plane is nearly perpendicular to the Milky Way's own disk. In other words, if you define up and down relative to the Milky Way's disk, then many of its satellite galaxies are arranged in a band that runs from above to below, like a belt cinched vertically around the galaxy's waist. This is called the plane of satellites, and it is one of the most puzzling features in modern astrophysics. In 2012, astronomer Marcel Paulowski, then at the University of Bonn, and his colleagues published a detailed analysis showing that at least 11 of the Milky Way's brightest satellite galaxies, including the Large and Small Magellanic Clouds, the Sagittarius Dwarf, and several of the classical dwarf spheroidals, orbit within a thin plane that is roughly perpendicular to the galactic disk. The plane is coherent. The satellites within it appear to be co-orbiting, moving in the same general direction around the Milky Way. And the plane's existence is difficult to explain. Standard cosmological models predict that satellite galaxies should be distributed roughly spherically around their host, not confined to a thin plane. The dark matter halos in which galaxies form are approximately spherical, and the smaller halos that become satellite galaxies should fall in from all directions, producing an isotropic distribution. The observed plane of satellites violates this expectation. Some researchers argue that the plane is a statistical fluke, a temporary alignment that will dissolve over time. Others argue it reflects a real physical process, perhaps the accretion of satellites along a cosmic filament that happened to approach the Milky Way from a particular direction. The debate is active. The data are ambiguous, and the plane of satellites remains one of those places where observation and theory do not yet agree. What matters for our vertical journey is the implication. The satellite galaxies of the Milky Way, the small, ancient, dark matter-dominated systems that orbit far above and below the galactic disk, are not randomly scattered through the halo. They appear to be organized, arranged in a structure that extends vertically, perpendicular to the disk. The space above and below the Milky Way is not merely populated, it is patterned. Andromeda shows the same phenomenon. In 2013, Rodrigo Ibata of the Observatoire Astronomique de Strasbourg and his collaborators reported that roughly half of Andromeda's satellite galaxies also lie in a thin plane, co-rotating around their host. Two major galaxies, two planes of satellites, two vertical structures, each perpendicular to its host galaxy's disk, each difficult to explain within the standard framework of galaxy formation. Now we rise above the local group entirely, and here the meaning of above and below begins to shift. Within the solar system above and below are defined by the ecliptic, the plane of the planets. Within the galaxy, they are defined by the galactic disk. Within the local group, they are loosely defined by the plane connecting the Milky Way and Andromeda. But at larger scales, scales of hundreds of millions of light years, these local reference frames dissolve. There is no universal up. There is no cosmic down. The universe at sufficiently large scales looks the same in every direction. This is the cosmological principle, the assumption supported by overwhelming observational evidence that the universe is homogeneous and isotropic on the largest scales. And yet, between the local anisotropy of the solar system and the global isotropy of the cosmos, there is a middle ground, a scale at which the universe is emphatically not uniform, at which structure extends in all directions, including vertically. That middle ground is the cosmic web. Picture the universe not as a smooth, uniform expanse of space, but as a vast, three-dimensional network, a web of matter stretching in every direction, with dense filaments of galaxies and gas connecting massive nodes. And between the filaments, enormous voids where almost nothing exists. This is the large-scale structure of the universe, mapped by surveys like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey, confirmed by simulations like the Millennium Simulation, run by Volker Springel and collaborators at the Max Planck Institute in 2005. The cosmic web is real. It is the skeleton of the universe. The filaments of the cosmic web are immense, hundreds of millions of light-years long, tens of millions of light-years wide. Where filaments intersect, galaxy clusters form, the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies, trillions of solar masses of dark matter, and vast reservoirs of hot intracluster gas. Where filaments are absent, voids dominate, regions hundreds of millions of light-years across, nearly empty of galaxies, containing only the thinnest possible traces of gas and dark matter. The local group sits within a filament. Specifically, it is part of a structure called the local sheet, a relatively thin concentration of galaxies that includes the Milky Way, Andromeda, and several dozen nearby groups. The local sheet, in turn, borders one of the largest known voids in the observable universe, the local void, a vast, nearly empty region stretching at least 150 million light-years across. The local void lies roughly in the direction perpendicular to the local sheet. If you define above the local sheet as the direction toward the void, then what lies above our neighborhood, at scales of hundreds of millions of light-years, is almost nothing. Emptiness, a volume large enough to contain thousands of galaxies, containing almost none. In 2019, astronomer R. Brent Tully of the University of Hawaii, who had spent decades mapping the local universe, described the local void as one of the dominant features shaping the motion of nearby galaxies. The gravitational effect of the void, or rather, the absence of gravitational pull from within it, causes the local sheet to accelerate away from the void, as if being pushed. This motion is real and measurable. The emptiness above our neighborhood is not passive. It exerts an influence, not through its mass, but through its lack of mass, sculpting the flows of galaxies on scales of hundreds of millions of light-years. And on the other side of the local sheet, in the opposite direction, below, if you will, lies the Virgo supercluster, the larger structure to which the local group belongs. The Virgo supercluster is itself part of an even larger structure called Laniakea, a supercluster of superclusters identified in 2014 by Tully and his collaborators. Laniakea spans roughly 500 million light-years, and contains approximately 100,000 galaxies. Its name comes from the Hawaiian words for immeasurable heaven. The cosmic web has no preferred vertical axis. A filament can stretch in any direction. A void can yawn open above, below, or to the side. But the web has structure, and that structure defines, at every scale, what exists in the directions perpendicular to the planes and sheets that matter tends to occupy. Galaxies live in filaments and sheets. Voids live between them, and the tension between the two, between the concentrated matter of the filaments and the near emptiness of the voids, is the vertical architecture of the universe itself. Something here deserves attention, because we have arrived at a moment where the question we started with, what really exists above and below our solar system, transforms into something deeper. We asked a simple question. We expected a simple answer. We thought we were asking about the space above and below a flat disk of planets. A geographic question, like asking what is north of your house. But the answer has led us through 8 nested layers of structure, each one larger and stranger than the last, until we have reached the cosmic web itself, the largest pattern in the observable universe. And at each layer, the same revelation repeated. The flat picture was incomplete. The vertical dimension was hiding in plain sight. The structures above and below were larger, older, and more consequential than the structures along the plane. Why does this pattern repeat? Why does this pattern repeat? Why at every scale, solar system, galaxy, cosmic web, does the universe insist on extending vertically far beyond the thin, bright planes that dominate our images? The answer is gravity. Gravity flattens things. Rotating systems collapse into disks because angular momentum prevents contraction along the spin axis, while allowing it perpendicular to the spin axis. The solar nebula flattened into a disk. The Milky Way's gas settled into a disk. Clusters of galaxies stretch along filaments that are themselves flattened sheets seen edge-on. But gravity also preserves the memory of what existed before the flattening. The Oort Cloud is spherical because its objects were scattered before the disk fully formed, and at those distances, there was not enough time or friction to flatten them. The stellar halo is spherical because its stars formed in an era before the disk existed. The dark matter halo is spherical because dark matter does not interact electromagnetically, and therefore cannot radiate energy and collapse into a disk. The vertical structures are the old structures. The flat planes are the new ones. When you look above and below, you are looking backward in time, not in the cosmological sense of redshift, but in the dynamical sense of formation history. The disk is the present, the sphere is the past, and the past, as it turns out, is much larger than the present. Is the Oort Cloud spherical shell a frozen snapshot of the solar system's earliest chaos? Is the stellar halo a fossil of the galaxy's formation before the disk settled into its present thinness? Is the dark matter halo the skeleton of a universe that never learned to flatten at all? Are the Fermi bubbles the galaxy's memory of an eruption that happened millions of years ago, preserved in gamma-ray light above and below the plane where the eruption occurred? Are the satellite galaxies, arranged in their strange vertical planes, tracing the pathways of ancient accretion events that built the Milky Way from pieces? And if the vertical dimension is where the past lives, if looking up and looking down means looking at older, larger, more primordial structures, then what does it mean that we, biological creatures confined to a thin disk of rock, orbiting within a thin disk of stars, can perceive these structures at all? What does it mean that a species living on a flat surface evolved to navigate in 2 dimensions, can deduce the existence of dark matter halos and circumgalactic media and Fermi bubbles that extend for tens of thousands of light years in a direction we cannot even point to with our fingers. Can we ever truly map the full vertical extent of the solar system's surroundings? Can we ever see the Oort Cloud directly, every one of its trillion frozen bodies? Or will it remain forever inferred, a theoretical construct supported by the trajectories of comets we happen to observe? Can we ever measure the heliosphere's shape from the outside? Or are we permanently trapped inside the bubble, guessing at its geometry from the inside? Can we know what the local bubble looked like before the supernovae carved it? Or is that information lost, scattered by blast waves, erased by the passage of 15 million years? We cannot know. Not fully, not with certainty. We are inside every structure we are trying to map. We are inside the heliosphere, inside the local bubble, inside the galactic disk, inside the dark matter halo. We are, in the most literal sense, trying to describe the shape of a room from the inside without ever being able to step outside and look at it. Every model of the heliosphere's shape, comet, bubble, croissant, is constructed from data gathered by instruments that are themselves inside the heliosphere. Every estimate of the Oort Cloud's population is extrapolated from the tiny fraction of comets that happen to fall inward and become visible. Every map of the local bubble's walls is assembled from measurements of starlight reddening, the dimming and reddening of light that passes through interstellar dust, which tells us where the dust is, but not necessarily where it was. There is an epistemological wall here, and it is worth sitting with. The vertical universe, the vast, layered, nested architecture above and below the ecliptic, is not something we have seen. It is something we have deduced. It is a portrait assembled from shadows, from statistical inferences, from the trajectories of particles and the dimming of starlight, and the faint glow of gamma rays that most humans will never directly perceive. The universe above us is real. The universe below us is real. But our knowledge of it is constructed, pieced together from fragments, and there are places where the fragments run out, and we are left with models, hypotheses, and honest ignorance. Once you see this, once you understand that every flat diagram you have ever been shown is a cross-section of a vastly deeper, more ancient, more layered reality, the entire picture inverts. The flat disk is not the solar system. It is the solar system's thinnest, most recent, most visible layer. The real solar system is a sphere. The real galaxy is a sphere inside a sphere, inside a cloud of hot gas, inside a dark matter ocean. The real universe is a web of filaments and voids extending in every direction, with no preferred plane at all. The flatness was never the truth. It was the shadow the truth cast on a page too small to hold anything more. And somewhere above you, right now, hundreds of thousands of light years above the bed or chair or floor where you are resting, a globular cluster is completing another orbit around the Milky Way. Its stars are 11 billion years old. They have crossed the galactic plane thousands of times. They have never heard of the ecliptic. They do not know that the solar system exists. And they will still be orbiting, still rising and falling through the galaxy's vertical axis, long after the sun has exhausted its fuel and faded into a white dwarf no brighter than a candle seen from across a continent. That is what exists above and below your solar system. Not emptiness, not void, but structure, ancient, vast, layered, and profoundly indifferent to the flat diagrams we draw to contain it. Stand on a hilltop, in your mind, on a clear night, the kind of night where the air is still and the horizon drops away and the stars seem close enough to touch. You have been to this hilltop before. Everyone has, in memory or imagination. The sky is a dome above you. The ground is solid beneath your feet, and between the two, you stand, a warm body in a cold universe, looking up. You know more now than you did when we began. You know that the dome is not a dome. It is a series of nested shells, the heliosphere's magnetic boundary, the local interstellar cloud's warm gas, the local bubble's carved-out void, the galaxy's thin disk and thick disk and stellar halo, the Fermi bubble's gamma-ray towers, the dark matter halo's invisible sphere, the circumgalactic medium's hot breath, the cosmic web's vast filaments and voids. Each shell is larger than the last. Each shell is invisible from inside the previous one. And you are inside all of them, standing on your hilltop, looking up through every layer at once. The stars you see, the ones that prick the darkness with their sharp, steady light, are almost all within the thin disk. They are your neighbors, cosmically speaking. Most of the naked eye stars lie within a few hundred light years, a tiny fraction of the galaxy's diameter. They are the thinnest, most local layer of the vertical architecture. Above them, unseen, the thick disk's old stars trace their high, slow arcs. Above those, the halo's ancient globular clusters orbit in three-dimensional paths that predate the disk. Above those, dark matter fills a sphere so large that the visible galaxy is a bright smudge at its center. Above all of it, the circumgalactic medium radiates faintly in X-rays, a hot atmosphere around a galaxy that does not know it has one. You cannot see any of this from your hilltop, but you can feel it, if not physically, then conceptually. The weight of all that structure, all that history, all that layered complexity, pressing down from above and pushing up from below. The solar system is not floating in emptiness. It is nested, cradled, wrapped in shells of matter and energy that stretch for hundreds of thousands of light years in the direction your finger points when you raise your arm toward the zenith. Stay with this for a moment. There is no need to climb higher or dig deeper. The layers are all present, all interpenetrating, all occupying the same sky you have looked at since childhood. The only thing that has changed is your awareness of them. Think about the rain. Not rain from clouds, rain from space. We spoke earlier of interstellar iron-60 found in Antarctic snow, atoms forged in ancient supernovae, drifting through the local interstellar cloud, slipping past the heliosphere's magnetic boundary, falling through the atmosphere and settling on ice. That rain has not stopped. It continues tonight. Right now, as you listen to this, particles from outside the solar system are entering the heliosphere. Cosmic rays, high-energy protons and atomic nuclei, accelerated by supernova remnants and other violent processes in the galaxy, are threading through the magnetic field above you, striking molecules in the upper atmosphere, producing showers of secondary particles that cascade downward and pass through your body. Roughly 1 muon, a heavy cousin of the electron, born from cosmic ray collisions in the upper atmosphere, passes through every square centimeter of your body every minute. These muons were born from particles that originated outside the solar system, above the ecliptic plane, in the galactic disk or beyond. The vertical universe is not abstract. It is passing through you, and the light. The starlight you see from your hilltop has traveled vertically as well as horizontally. The light from a star near the galactic North Pole has come to you from above the disk, through the thin gas of the halo, through the local bubble's void, through the heliosphere, through the atmosphere, and into your eye. It has crossed every layer we discussed, in reverse order on its way to your retina. You are not merely looking at the vertical universe. You are receiving it. It is arriving, photon by photon, and your eye is the end point of a journey that began thousands of light years above the galactic plane. The quiet is what strikes you, standing on that hilltop. The universe above is violent. Supernova carving bubbles, black holes inflating gamma-ray towers, cosmic rays screaming through magnetic fields at nearly the speed of light. But none of it makes a sound. The violence is silent. The rain is invisible. The layers are transparent. The only evidence of the vertical universe from your hilltop is the faint, steady light of the stars and the occasional streak of a meteor, a grain of Oort Cloud dust, perhaps, finally completing a journey that began before the human species existed. Breathe in. The air in your lungs contains atoms that were once part of the interstellar medium. Every oxygen atom you breathe was forged in a massive star and expelled in a supernova, drifting through the galaxy's vertical structure for millions of years before settling into the molecular cloud that collapsed to form the sun. The nitrogen, the carbon, the iron in your blood, all of it passed through the layers above and below. Through the circumgalactic medium, through the halo, through the disk, before arriving here in this body, on this hilltop, in this moment. You are not separate from the vertical universe. You are made of it. The hilltop is enough. You do not need to travel to the Oort Cloud, or the heliopause, or the Fermi bubbles to encounter what exists above and below. It is here. It has always been here. The only thing the journey has given you is the ability to name the layers, to feel their depth, to understand that the sky is not a ceiling, but a corridor, one that extends in both directions farther than the human mind was built to comprehend. Now we turn to the deepest question this journey raises. Not a question about the structures themselves, but about what they mean. There is a painting in the Museo del Prado in Madrid. It was made by Hieronymus Bosch sometime around the year 1500, and it is called The Garden of Earthly Delights. The painting is a triptych, 3 panels hinged together. When the panels are open, the viewer sees a dazzling, bewildering panorama of creation, pleasure, and damnation, spread across a landscape that stretches from the earthly to the divine to the infernal. But when the panels are closed, when the triptych is shut, as it would have been most of the time, since it was an altarpiece meant to be opened only on special occasions, the exterior shows something entirely different. It shows the earth, or rather, it shows a sphere, a transparent globe, half filled with water, plants beginning to emerge on its surface, suspended in darkness. It is the 3rd day of creation, according to the book of Genesis. The world is new. Life is just beginning, and the sphere floats in a void, alone, with no context, no surrounding structure, no hint of what lies beyond its fragile shell. For 5 centuries, that image has resonated with viewers, and not only for its religious content. It captures something universal, the feeling of being inside a sphere, looking out at darkness, unable to see what lies beyond the boundary. Bosch painted it in an era when the structure of the cosmos was a matter of theological speculation, when the idea of a heliosphere, or an Oort cloud, or a galactic halo would have been inconceivable. But the emotional truth of the image has not aged. We are still inside the sphere. We have simply learned that the sphere is nested, that outside one boundary lies another, and another, and another, each one revealing a larger, older, more mysterious cosmos. The history of astronomy is, in a very real sense, the history of discovering new layers above and below. For most of human history, the sky was a solid dome. The firmament, a crystal sphere to which the stars were fixed. Above the dome was the realm of the divine. Below the earth was the underworld. The vertical axis was the axis of meaning. Heaven above, hell below, humanity in between. Copernicus dissolved the crystal sphere, but replaced it with a new boundary, the sphere of fixed stars, still imagined as a thin shell at a finite distance. Herschel, in the late 18th century, used star counts to show that the Milky Way had depth, that the stars were not on a shell, but distributed through a vast, flattened system. Kapteyn, in the early 20th century, mapped the galaxy as a lens-shaped island of stars, roughly 40,000 light-years across, with the Sun near the center. Shapley corrected Kapteyn's map in 1918, using the distances to globular clusters to show that the Sun was not at the center of the galaxy, but far out in its disk, and that the galaxy was much larger than Kapteyn had believed. Hubble, in 1924, proved that the Andromeda Nebula was a separate galaxy, shattering the idea that the Milky Way was the entire universe. Each discovery added a new layer. Each layer was above and below, extending the vertical dimension of the known cosmos far beyond what the previous generation had imagined. And each discovery carried the same emotional charge. The realization that the boundary you thought was the edge of everything was, in fact, a local feature. A wall inside a larger room, a shell inside a larger sphere. Oort's 1950 proposal of the cometary cloud extended the solar system's vertical reach from tens of astronomical units to tens of thousands. The discovery of the local bubble in the 1970s and 1980s revealed that interstellar space near the Sun was not uniform, but structured, carved by explosions, shaped by stellar deaths. The Fermi bubbles, discovered in 2010, showed that the galaxy itself had a vertical dimension far larger and more energetic than the disk alone would suggest. Each revelation followed the same pattern. You think you know the shape of the space you inhabit. You learn you are wrong. The space is deeper than you imagined. It extends above and below, and it has been there all along. This is the pattern that connects Bosch's painted sphere to the IMAP spacecraft orbiting Lagrange Point 1. The human species lives inside nested shells, and our history is the history of learning to name them. Each shell, when first encountered, feels like the final boundary, the last layer, the true edge. And each time we discover that the edge is not an edge at all. It is a transition zone between one structure and the next. The heliopause is not the end of the solar system. It is the beginning of the interstellar medium. The wall of the local bubble is not the end of the void. It is the beginning of the denser galaxy beyond. The edge of the dark matter halo is not the end of the Milky Way's influence. It is the beginning of the circumgalactic medium, which blends, gradually and without clear boundary, into the intergalactic medium, which is itself structured by the cosmic web. There is no final shell. Or if there is, we have not found it. The observable universe has a boundary, the cosmic microwave background, the surface of last scattering, roughly 46 billion light-years away in every direction. But that boundary is not a wall. It is a horizon, a limit of perception, not a limit of reality. Beyond it, the universe almost certainly continues. It may continue forever. It may be infinite. And if it is infinite, then the vertical direction, straight up from the ecliptic, straight up from the galactic plane, straight up from the local sheet, straight up from the filaments of the cosmic web, extends without end. There is no ceiling. There is no floor. There is only structure, layered and nested and vast, fading gradually into the unknown. The existential weight of this should not be underestimated. Every human civilization has defined itself in part by its relationship to what lies above and below. The Egyptians built pyramids aligned to the stars, vertical monuments reaching toward a vertical cosmos. The Greeks imagined a layered universe of crystalline spheres, each one above the last, with the prime mover at the top. Dante structured his entire cosmology around the vertical axis. Hell below, purgatory in the middle, paradise above. Even in the secular scientific age, we speak of looking up at the stars as if the stars were above us, when in truth, they surround us in every direction, and the very concept of above is a local accident defined by the direction opposite to gravity on the surface of this particular planet. But the accident is not meaningless. The fact that gravity defines a local vertical, that there is on the surface of Earth a real and physically meaningful up and down, connects us to the largest structures in the universe. Gravity is what flattened the solar nebula into a disk. Gravity is what settles the Milky Way's gas into a thin plane. Gravity is what pulls the sun back toward the galactic midplane every 30 million years. Gravity is what shaped the cosmic web into filaments and voids. The same force that tells your body which way is down is the force that builds every layer of the vertical universe above and below you. The local vertical is not arbitrary. It is a thread, a single thread in the gravitational web that connects your body to the architecture of the cosmos. And so the question we asked at the beginning, what really exists above and below our solar system, turns out to be a question not just about geography, but about identity. You are a creature of the disk. You live on a flat surface, orbiting within a flat plane inside a flat galaxy. Flatness is your native geometry, but you are made of materials that came from the spherical structures, from the Oort Cloud's scattered ice, from the stellar halo's ancient supernovae, from the circumgalactic medium's accreted gas. The vertical universe built you. The flat disk merely holds you. This is the tension at the heart of the human relationship with the cosmos. We are flat creatures in a spherical universe. We draw flat maps of curved spaces. We print flat diagrams of layered structures. We evolved to navigate two-dimensional surfaces, the savanna, the coastline, the river valley, and we struggle instinctively to conceive of the full three-dimensional depth of the space we inhabit. The textbook poster of the solar system is not merely a simplification. It is a confession, an admission that the human mind defaults to flatness, that we see the ecliptic because the ecliptic is the plane we live in, and that everything else, the Oort Cloud, the heliosphere, the bubbles and halos and voids, must be imagined, deduced, inferred, because we cannot perceive it directly. The fact that we have deduced it anyway, that we have, through centuries of painstaking observation and mathematical reasoning, reconstructed the full vertical architecture of the cosmos from inside a thin disk on the surface of a small planet, is itself a kind of miracle. Not a supernatural one, a cognitive one. The human brain, a kilogram and a half of tissue evolved to track predators and find fruit, has mapped structures that extend for hundreds of thousands of light years in a direction it cannot point to. It has inferred the existence of 1 trillion frozen bodies it has never seen. It has measured the shape of a magnetic bubble from the inside. It has detected the gamma-ray glow of structures 25,000 light-years above the galactic center, using instruments that fit inside a satellite the size of a car. The vertical universe did not reveal itself willingly. It was dragged into the light by human ingenuity, one layer at a time, across centuries of effort. And the dragging is not finished. IMAP is mapping the heliosphere right now. Future telescopes will map the circumgalactic medium in greater detail. Future simulations will refine our understanding of the Oort Cloud structure. Each new layer, when it comes, will extend the vertical dimension further, deeper, higher, more complex than we currently imagine. There is no reason to believe we have found the last layer. There never has been. So now we return to where we began. The poster, the classroom wall, the sun in the middle, fat and yellow, the planets trailing outward in concentric rings. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune. A flat wheel on a flat page, clean and orderly and profoundly incomplete. You know now what the poster left out. You know about the Kuiper Belt's thick, puffy torus. Not a flat ring, but a cushion of icy bodies tilted at wild angles, rising and falling billions of kilometers above and below the ecliptic. You know about Sedna, tracing its lonely 11,000-year orbit through the vertical no-man's land between the planets and the Oort Cloud. Its very existence, a clue that the space perpendicular to the disk is structured and storied. You know about the Oort Cloud itself. Jan Oort's great inference, 1 trillion frozen bodies forming a spherical shell that reaches 1.6 light-years in every direction, dwarfing the planetary disk by a factor of thousands, extending more than 1/3 of the way to the nearest star. You know that the solar system is not shaped like a disk. It is shaped like a marble, dark, frozen, ancient, with a thin, bright line of planets running through its center. You know about the heliosphere, the magnetic bubble blown by the solar wind, pressing outward in every direction, its shape still debated, still mysterious, now being mapped with unprecedented precision by the IMAP spacecraft at Lagrange Point 1. You know that Voyager 1 crossed its boundary in 2012 and Voyager 2 in 2018, and that both found an interstellar magnetic field far stronger than anyone had predicted, strong enough to reshape the bubble's geometry from the outside. You know about the local interstellar cloud, the local fluff, that warm, thin wisp of partially ionized gas flowing from the direction of Scorpius and Centaurus, through which the sun has been drifting for tens of thousands of years. You know that atoms from this cloud, interstellar iron-60 forged in ancient supernova, have been found in Antarctic snow. The rain from above is real. It falls on you even now. You know about the local bubble, the 300 light-year void carved by roughly 20 supernova explosions over the past 10 to 12 million years, a wound in the galaxy's interstellar medium that the sun entered 7 to 8 million years ago. You know that the bubble extends above and below the galactic plane, possibly venting hot gas through chimneys that connect the disk to the halo. You know about the sun's vertical oscillation through the galactic midplane, the slow, stately bobbing with a period of roughly 52 to 74 million years, driven by the gravitational pull of stars and gas and dark matter concentrated near the plane. You know that we are currently near the top of our bounce, roughly 65 to 100 light-years above the midplane, drifting upward before the long fall back. You know about the Fermi bubbles, those colossal towers of gamma-ray energy, 25,000 light-years tall, rising from the galactic center in directions perpendicular to the disk, discovered in 2010 by Su, Slatia, and Finkbeiner. You know about the even larger Aerosita bubbles glowing in X-rays beyond them. You know about the dark matter halo, invisible, immense, extending 300,000 light-years or more in every direction, outweighing all visible matter 6 to 1. You know about the circumgalactic medium, the galaxy's hot atmosphere, perhaps 600,000 light-years across, fed from below by supernova-driven winds, and from above by the slow accretion of intergalactic gas. You know about the Magellanic Stream, that river of hydrogen trailing below the galactic plane, feeding the Milky Way with fresh material for future stars. You know about the cosmic web, the filaments and voids that structure the universe at the largest scales, the local void yawning open in one direction, the Virgo supercluster and Laniakea stretching in another. You know that at the largest scales, the universe has no preferred vertical axis, that above and below are local concepts, defined by the accidents of gravity and rotation, meaningful only within the nested reference frames of the planet, the solar system, and the galaxy. And you know, perhaps most importantly, that the vertical structures are the old structures. The flat disks are recent. The spheres are ancient. When you look above and below, you are looking at the past, at the Oort Cloud's memory of the solar system's chaotic birth, at the stellar halo's memory of the galaxy's formation, at the dark matter, halo's memory of a universe that existed before any disk, any plane, any flat structure at all. The vertical dimension is where the past lives, and the past, it turns out, is much larger than the present. That poster on the classroom wall was never meant to deceive. It was meant to teach, to give young minds a foothold in an overwhelmingly complex cosmos. And it succeeded. Generations of children learned the names of the planets, the order of the orbits, and the basic architecture of the solar system from that flat, bright image. The deception was unintentional. The page was flat, and so the diagram was flat, and the vast, three-dimensional, layered, nested spherical reality of the space above and below was quietly omitted, not out of malice, but out of the simple impossibility of printing a sphere on a sheet of paper. But now you see past the poster. You see the Oort Cloud's dark sphere wrapping around the bright disk. You see the heliosphere's magnetic cocoon pressing outward against the interstellar wind. You see the local bubbles void, the galaxy's disk and halo, the Fermi bubble's vertical towers, the dark matter's invisible ocean, the circumgalactic medium's hot breath. You see the cosmic web stretching in every direction, filaments and voids, structure without end. And perhaps the next time you look up at the night sky, from a hilltop, from a window, from a quiet place where the stars are visible, you will feel something different. Not just the beauty of the stars along the plane, not just the faint glow of the Milky Way stretching from horizon to horizon, but the depth, the vertical depth, the knowledge that the sky above you is not a dome, but a corridor, and that corridor extends through shell after shell after shell, each one larger and older and more silent than the last, all the way to the edge of the observable universe, and almost certainly beyond. The textbook diagram is still useful. The planets still orbit in their thin, bright plane. Mercury still bakes, Neptune still freezes, and Earth still turns, steady and blue, in the habitable zone. Nothing about the vertical universe changes the beauty or the precision of that flat, familiar picture. But the picture is a cross-section. It is a single slice through a reality that extends, above and below, into structures so vast and so ancient that the human mind can hold them only briefly before they slip away, like a dream dissolving in the first light of morning. That is what really exists above and below your solar system. Not emptiness, not nothing, but layer upon layer of structure, frozen comets and magnetic boundaries and interstellar clouds and supernova-carved voids and oscillating stars and gamma-ray towers and dark matter oceans and hot galactic atmospheres and cosmic filaments and incomprehensible voids. All of it stacked above your head and mirrored below your feet. All of it invisible. All of it real. all of it older than the ground you stand on. If this changed how you think about the night sky, if the space above you feels a little deeper tonight, a little more layered, a little more alive, then the time was well spent. Thank you for staying through every layer. Thank you for climbing this far. The sky will be there when you close your eyes, and it will still be there, deeper than any poster could show, when you open them again. Rest now. The vertical universe will keep